In this video, we're going to go over section 2.7 from our textbook, which goes over marginal analysis. So this is one important application to business and economics. And in economics, the word marginal will refer to the rate of change, i.e. to a derivative. So here's our formal definition of marginal cost, revenue, and profit. So X will be the number of units of a product produced in some given time interval. Then our total cost is going to be given by C of X, and then the marginal cost will be the derivative of our total cost, so C prime of X. Similarly, our total revenue is going to be R of X, and to find the marginal revenue, we will take the derivative of our revenue. And lastly, the total profit here is going to be our revenue minus the cost that it takes to make the certain product. And then the marginal profit will be the derivative of our revenue minus the derivative of our cost, or the marginal revenue minus the marginal cost. All right, so we'll look at an example of this. So a company manufactures automatic transmissions for cars, and the total weekly cost in dollars of producing X number of transmissions is given by this cost function here. The first thing we want to do is find the marginal cost function. So this is part A. So all we have to do here is take the derivative of our cost function. So we have C of X here, and what we'll do is take the derivative of each individual term here. So the derivative of 50,000, this is just a constant, so we know that's just going to be 0. So we're not going to write anything for that one. Looking at 600x, we can use our power rule. Remember, we have 600 times x to the power 1, so that 1 comes down in front. So then we have 1 times 600, so we just have 600 in front. And then we have x to the power 1 minus 1, which is just x to the power 0, so we don't have an x term there. Then for this second term here, we're going to subtract the derivative of this guy. So we have 0.75 times 2, because our power 2 is going to come in front. And then we have a remainder of x because our power is going to be 2 minus 1, so x to the power 1. And so we get 600 minus 1.5x. And so that is our marginal cost function. Now for part B, we want to find the marginal cost at a production level of 200 transmissions per week. So what we'll do here is plug that value into our marginal cost function. So our x value is 200 here. So you get 600 minus 1.5 times 200. So we get 600 minus 300, which is just 300. Then for part C, we want to interpret these results here. So we know that looking back at this definition here, our marginal cost or revenue or profit, but in this example, marginal cost, is going to be the instantaneous rate of change of cost relative to production at a given production level. So our current production level is 200 transmissions per week. And since we got that the marginal cost at that production level is equal to 300, what this means is the total cost with respect to production level of 200, and I'm going to abbreviate with respect to as WRT. So that's with respect to production level of 200 transmissions per week is going to be increasing at a rate of $300 per transmission. Let's see if that is that. All right, so that is what that means there. Now for part D, we're asked to find the exact cost of producing the 201st transmission. Now, before we get into that, I want to put a note here. So our cost function here represents the total cost of producing X amount of items, not the cost of producing a single item. Okay, so we have to be careful with that. So what this means is, let's look at a quick example. The total cost of producing 2 items, so total cost to produce 2 items would be C of 2, so we'd plug 2 into our cost function for X. And then the total cost of producing 3 items would be C of 3. So we're plugging 3 into X into our cost function. But the total cost of producing the third item is going to be C of 3 minus C of 2. So we're taking the total cost of producing this guy and then subtracting out whatever it costs to make the 2 before it, so we can look at the exact cost of the third item. So this means our formula for exact cost of producing the X plus 1 or the X plus 1st item is going to be given by this formula here. And don't let this notation fool you. In this little example that we did, X was 2. So we have C of X, C of 2, and then C of X plus 1 is just going to be 2 plus 1, so whatever your X is. So in this case, it was 3. So going back up to part D, we want to find the exact cost of producing the 201st transmission. So what we'll do there, we know that this is going to be C of our X plus 1, so 201 minus C of 200. So first, we'll plug in 201 into our cost function. And so this will be 50,000. So we're plugging into this function here. So plus 600 times 201 minus 0.75 times 201 squared. All right, then squaring this, multiplying by this, and taking the total there, we get 140,299.25. And then doing the same thing where X is now equal to 200. So plugging it into our equation. We get 140,000 exactly. It's a comma. All right, so then this tells us that the exact cost for the 201st transmission is going to be $299.25. All right, and if you notice, this is pretty close to the cost that we got at a production level of 200 transmissions per week. We got that this cost would be increasing at a rate of $300 per transmission. So the next transmission, it would cost an additional $300 to make, and that is pretty close to what we got here. Okay, so that leads us to this next theorem here. and it tells us that the marginal cost here, so our derivative of our cost function, is pretty close to or approximately equal to our exact cost minus our cost function. Yep, and that's exactly what we showed here. So if you're ever trying to find this, you can always check your answer with what you got for the marginal cost at the given production level. Okay, so now we are going to look at an application where we discuss how price, demand, revenue, cost, and profit are tied together in certain applications. So we're given this example here. So a company's market research department recommends the manufacture and marketing of a new headphone. After certain test marketing, the research department presents the following price-demand equation. So we're given that X is equal to 10,000 minus 1,000 times P, where X is our demand at a certain price, P. Then solving for P, we also get another equation, so another way to represent this. So this tells us that our price is equal to 10,000 minus 0.01 times X, where X is our certain demand. Right, so X is the number of headphones that retailers are likely to buy at a given price, P. So then we're also given the cost function here. So 7,000 is the estimate of fixed costs, and $2 is the estimate of variable costs per headphone. So the first thing we want to do here is find the domain, defined by the price-demand equation 2. So we're looking at this equation here. So I'll write that down here. All right, so we want to find the domain. And then something to note here is that we're talking about the price of something and we're talking about the demand of something. So immediately we know that X, our demand, is never going to be negative, and our price can never be negative either. So this tells us that this is going to have to be greater than 0. However, we can have that our demand is 0, but no one wants these headphones. So it's not going to be strictly greater than 0, it's going to be greater than or equal to 0. All right, then solving for X, we get this, and then we'll divide by 0.01, so we'll get 10,000 is greater than X. And then this tells us our domain is X is going to be in between 0 and 10,000. All right. For part B, we want to find and interpret the marginal cost of, or the marginal cost function. So we're given this is our cost function, and the marginal cost is just going to be the derivative of that. So C prime of X. And if you notice, the derivative of 7,000 is just 0, and then the derivative of 2x is just 2. So we have here a constant function. So this tells us, essentially this tells us that the cost is going to increase by $2 for every new headphone made. So it's going to be constantly increasing by $2. So I'll write that here. For every new headphone made. All right, so that's how we interpret that. Next, we want to find the revenue function as a function of X and find its domain. So we know that our revenue is going to be equal to the amount of money received for making an X amount of headphones at a certain price P. So this tells us this is going to be equal to number of headphones sold, so number of headphones sold, times the price per headphone. And we know that the number of headphones sold is just going to be X, and the price is going to be P. Now, something to note here is that what we can do in this case is just plug in, because we do want to have just one variable here. We can plug in what we have for X. Our equation for X was 10,000 minus 1,000 times P. So we can write this as times P, and this could be our revenue function. However, in this question, it did ask us to write our revenue function as a function of X. Additionally, up here, we are told that in a price-demand equation, it is common to use demand as the independent variable when revenue, cost, and profit are also involved. So in this case, what we're going to do instead is write our revenue function as a function of X. So we will plug in this equation for P into our function. So this tells us we have a function of X. So we have X times our P, which was, 10 minus 0.001 times X. And then just distributing this X, we get 10X minus 0.001 X squared. All right, and then I do think it asks us to find its domain, but in this case, we do know that the domain for our equation P up here was this. And so all we did was multiply that by an X here, so it doesn't change our domain. We still need that our demand is going to be 0, and it can't be 0 or greater, and it can't be negative. Yeah. All right, and lastly, we are asked to find the marginal revenue at these given points here. So when X is equal, or when our headphones are equal to 2,000, 5,000, and 7,000. So all that means here for part D is we're going to plug those values into our marginal revenue function. So the first thing we have to do is find the domain of our revenue function, the derivative of our revenue function. So we know that this guy is just going to be 10. Using the power rule here, we will get 0.001 times 2 times X. So we get 10,000 minus 0.002X. Then at the given points, so X is equal to 2,000, we'll just plug this into our marginal revenue function. And in this case, we get 6. And doing the same thing for our other points, we have that X is equal to 5,000. So plugging that in, we get 0. And lastly, we'll look at X is equal to 7,000. And we get negative 4. All right. So that was that example. All right. So this leads us to this definition. So again, X will be the number of units of a product produced in some given time interval. Then our average cost is going to be denoted with this function C of X with a bar over it. So you can say this as C bar of X. So we're going to take C bar of X divided by the number of units of product that was produced. So again, we're just taking the average. And then the marginal average cost is going to be C prime bar of X. And we'll get that by finding the derivative of our average cost, not by taking the derivative of C of X and then dividing by X. And then similarly for the average revenue and marginal revenue and average profit and marginal profit. So we'll look at this example. We're given the cost function for the production of headphones that we just saw in example 3, and we want to find C bar of x and C prime bar of x, or in other words, our average cost and our marginal average cost. So our average cost is just going to be our cost function divided by x. So you can leave it as that, or we can write it as, all right. Now we want to find our marginal average cost. So we're going to take the derivative of this guy up here. And then what we'll do too is rewrite this so it's easy to see what we're doing with our power rule when we find the derivative. So the derivative of this guy, our negative 1 is going to come down in front and multiply our 7,000. So we get negative 7,000, and then we get negative 1 minus 1, so we get negative 2 in our exponent. And then we know that the derivative of a constant is just 0. So our marginal average cost is going to be rewritten with positive exponents, negative 7,000 over x squared. All right. Now for part B, we want to find our average cost when we have 100 headphones, and then our marginal average cost when we have 100 headphones, and interpret these values. So plugging in 100 for x, we get 7,000 over 100 plus 2. So we'll get 70 plus 2, so 72. Then doing the same thing for our marginal average cost. We get negative 7,000 divided by 10,000. So that's equal to negative 0.7. Now interpreting these values, I'll write down a little blurb here. So we see that at a production level of 100 headphones, the average cost of production is going to be $72. Okay? So at a production level of 100 headphones, the average cost of production is going to be $72. And then remember, when we look at our marginal cost, that's going to be the rate that it is changing. So looking at our marginal average cost, we have that, I'll write it like this. At this point, this cost is decreasing at a rate of 70 cents per headphone. And it's decreasing because we have negative here. All right. And lastly, we want to look at the results that we just talked about to estimate the average cost per headphone at a production level of 101 headphones. All right, so again, we know that the marginal average cost at this production level is decreasing at a rate of 70 cents per headphone. So if we're going to go from 100 headphones to 101, we know that the price is decreasing at this much. So at 101 headphones, the price is going to be 72 minus our 70 cents. And then this is going to be $71.30. All right, so that is it for this video.